I thought number 6 would be another good one to do from section 1.9. So let's read the instructions first. This one's another kind of challenging one. It says determine if the specified linear transformation is 1-to-1 A and then on to B. All right, so here are the conditions on the linear transformation. First question, is T 1-to-1? Okay. Now you might recall, and here's a theorem I'm going to throw at you again, and if you don't recall, try to remember it. T is 1-to-1 if and only if T of x equals 0 has only the trivial solution. All right, and the trivial solution of that is just the 0 column vector. And that's equivalent to saying, by the way, that T is 1-to-1 if and only if the columns of matrix A, the standard matrix, are linearly independent. But let's just focus on this particular version of that. T is 1-to-1 if and only if T of x equals 0 only has the trivial solution. Okay. And that's really equivalent to saying T is 1-to-1 if and only if this only has the trivial solution. So let's see if that's true. All right. By the way, you might recall that the definition of 1-to-1 basically says, I'll put that off to the side, if T is 1-to-1, then it means whenever this is true, and you might recall this from college algebra, that implies that this is true. If this is always true, whenever the two images are the same, that implies the original vectors are the same, that means T is 1-to-1. That's the definition. But our theorem says that it's enough for us to just check to see what the solutions of this equation look like. If we only get the trivial solution, then T is 1-to-1. If we get other solutions, then it is not 1-to-1. So that's how we're going to solve this problem, part A. All right. And notice, by the way, that they do give us the images of the columns of the identity matrix in R3, because that's the first column of the identity matrix in R3, that's the second column, and so on. And you might recall from the last problem I did that you can always get the standard matrix just by taking the images of the columns of the identity matrix in Rn, in this case R3. So it looks to me like A, well, the first column is 1, 4. Okay. Second column is 3, -6. Third column is -4, 2. So there's our A. And so we want to see what kind of solutions this equation has. And that is a system of equations, all right? Let's just jump straight to the augmented matrix of that system. I know the augmented matrix looks like this. All right, so let's try to put this thing in reduced echelon form and see what happens. Well, I want to make this a 0, so I'll multiply the first row by -4, add it to the second row. This times -4 is -12, minus 6 is -18. This times -4 is 16, plus 2 is 18, and the zeros don't change anything. Okay. And I guess it'd be a good idea to go ahead and divide the second row by -18. I'll go ahead and put it in reduced echelon form. All right. Next step is to turn that 3 into a 1. We know how to do that. So I'd multiply the second row by negative 3 added to the first row. But negative 3 times that is 3, minus 4 is negative 1. Okay. So notice that it looks like we have a free variable because we only have 2 pivot columns. So we do have a free variable here. That means there are infinitely many solutions. So there is more than just the trivial solution of the equation. So we have infinitely many solutions. Of AX equals 0. But remember, it's only 1-to-1 if you only have the trivial solution. So this thing is not 1-to-1. That's the answer to part A. All right? All right, now part B says, is T onto? Okay. And let's go back to the original information in the problem. So it looks like T takes vectors in R3 to vectors in R2. So what does it mean for a mapping to be onto? It just means that for every vector in R2, there exists a vector in R3 such that T of that vector gives you that vector in R2. So it maps to everything in R2. That's what it means to be onto. All right, so let's see if we can decide whether this thing is onto. Well, one way to decide that, I suppose, is to just let this be an arbitrary vector in R2, because that's the image space, all right? So the question is, can we find a vector x that's in R3 such that T of x is equal to that B1, B2 vector? That's really the question. Because if that's true, then we can always, this will always be in the image of some vector x in R3, if that's true. But remember, the left-hand side is really just AX. So we're trying to solve this thing if we can. But we already know what A is. Let's see. From previous notes, we have the A. From the first part of the problem. And here's our X, as always. It's actually a vector in R3, so I better have 3 variables there. So again, the big question is, given the B's, can we find the X's that will make this true? If the answer is yes, for arbitrary B's, then this is onto, right? And notice, by the way, the products are defined here because this is a 2 by 3 and this is a 3 by 1. So those numbers on the inside do match up, and you end up with a 2 by 1 vector in R2. So that looks good. So let's try to find the x1, x2, and x3. And so we need to write down our augmented matrix. It's really very similar to what we did in part A, I suppose, except we're going to have those B's in there. Okay. So I'm just going to do what I did before, essentially. It's just going to involve some of the B's. But I'm going to multiply the first one by -4, add it to the second one. -12 minus 6 is -18. 16 plus 2 is 18. Now here we want to say -4b1 plus b2. Okay. Now I suppose we could go ahead and divide the second row by -18. Just like we did before. This is just going to get a little messier. Okay, now multiply the second row by -3 and add it to the first row. So let's do that. So -3 times this is 3. If I add that to -4, I get -1. Now I'm going to multiply this thing by -3. So when I do that, let's see. Well, that'll just give me a +6 on the bottom. Okay. But I need to add that to B1. And I'm not sure I want to simplify it. I'm just going to leave it in that form. It's a little messy. Okay. But the point is, it looks like you do have solutions of this system. All right, so it looks like it is onto. So it wasn't 1-to-1, but it is onto. Because I was able to solve that system. I actually end up with infinitely many solutions because, once again, x3 is a free variable. But these are just given constants because the b's are given, remember. But we can find x1, x2, and x3 that'll satisfy that equation, that system. So T is onto.